This is a video on the learning map I have done for energy transfer and efficiency. Okay, so when it comes to energy, you need to know the 9 different types. And you also need to know the law. Now, a law means it's fact, it always happens. So the law of conservation of energy is that energy cannot be created or destroyed, only transferred in form. This sometimes comes up as a tick box exercise, and you have to tick the right one. So basically, the amount of energy that's around now was around at the Big Bang. It's constant, okay? So the 9 types of energy you need to know about are light, sound, nuclear, elastic potential, because you can store it, chemical energy, which isn't just in coal, it is in food as well, kinetic, anything moving, gravitational potential, when you lift anything up, it's also a type of stored energy, electrical, and thermal energy. Okay, I came up with a story to help you remember these. Okay, so I got home one day and I went into my bedroom and I turned the light on and I could hear a sound. I'd left the TV on and it was a news article about Chernobyl or the nuclear disaster that went on there. Oh, my sock fell down, the elastic's gone in it. So I pulled that back up and I thought to myself, I'm really, really hungry. I could do with some food right now. So I ran down the stairs and saw a loaf of bread on the side of the counter. Went to pick it up and because I'm clumsy, it fell onto the floor. Oh, picked it up, thought, I know, I'll use a toaster, I'll make some toast. Put the bread into the toaster, good old thermal energy, maybe some really lovely toast. So it's just a way to help you, because sometimes people can remember 8 or 7 of them, but not all 9. Now, when it comes to energy transfers, you always have an input energy, so that's what you start with. Then you'll have an arrow, and you have your output energies. It doesn't just have to be 1, it can be 2, it can be 3, it can be 4. But what you've got to ask yourself is it useful? Has that energy got a purpose in the transfer? Or is it wasted? Does it not have a purpose, so you didn't really need it? So for example, a light bulb, your input energy would be electrical, and that would be transferred into light. So that's useful because you use a light bulb to have light. But it would also transfer thermal energy. Now that's wasted because you do not put a light bulb on to heat your room up, okay? So that would be for your energies. Now efficiency, they can sometimes represent this as Sankey diagrams. They love to put these on every other year or so. There was one on last year, but the fact you need to remember is that the arrow width, so here and here, is proportional to the percentage of energy that's been transferred. So you start with 100% here. These 2 arrows would add up to the width of this one, okay? So even if I didn't have any numbers, I could roughly look at it and go, well, that's 80%, that's 20%. Now, a trick they do like to do is to not give you any numbers whatsoever. And then people go, well, I can't work out the efficiency. But if there's no numbers given to you, what you have to do is count the squares, because it's usually given to you on graph paper. So that's really important. And 1 would just equal 1 because it's all proportional. Efficiency itself is useful energy transferred, so it might be more than 1, so don't let that trick you out as well, divided by the total energy supplied. So what was the input energy? Now, there's 2 ways you can do this. You either leave the answer as a decimal, because it will be a decimal, because whatever you get out is going to be less than what you put in. Or if you want to, you can times it by 100, but please don't forget to add the percentage, because if you just put, for example here, 80, you'd lose them all automatically. These questions are usually worth about 2 marks. Specific heat capacity has come up on every single P1 paper for the last 5 years. Doesn't mean that it'll necessarily come up this time, but it has come up a lot, okay? 20% of your paper is going to be calculations. There's not that many they can ask you on for P1. Specific heat capacity is basically the amount of energy needed to raise the temperature of 1 kilogram of material by 1 degree C. So they all have different numbers because they all have different densities, okay? As you see, liquid has a lot higher than solid because the particles are further apart. The formula for specific heat capacity, I really like this one, is E, so energy, has to be in joules. If in the question they give it in kilojoules, they're trying to trick you. Put it into joules, times it by 1,000, add 3 zeros. Equals the mass in kilograms times the specific heat capacity. Last 2 years, they've asked you to remember this. Joules per kilogram centigrade, because you've had to work out specific heat capacity. Times the temperature change in degrees C. Now for this, they could tell you the temperature change, or they could give you 2 temperatures and you have to actually work it out yourself. Now, this is how it's given to you in the exam. If you get a question in the exam, please just write this out and put the numbers in. Even if they're asking you to work out temperature or specific capacity or mass, just put the numbers in and automatically that is 1 mark for you. Then do your rearranging. Now this would be a formula triangle, E over M times C times lambda, the temperature change. If you can remember that, or just rearrange it. Now, please never put something divided by E. E is always on top, okay? Always, always. So if I was trying to work out mass, I'd bring down specific heat capacity and temperature change, put that round there. If I was trying to get specific heat capacity, I'd bring these two down here. Like, you just cover them up, okay? But don't get tricked out by that. U value. They quite like for 1 mark to ask you what a U value is, and because people don't generally know. It's how effective a material is as an insulator, basically. How good is it? Now, when it comes to U values, a low U value is good. It means it lets less energy out, whereas a high U value means it transfers more energy. So it's not good for insulating your homes. This came up last year as the 6 marker, so it could come up smaller this year. You need to be aware of ways to insulate buildings. So you have cavity wall insulation, double glazing, you also have triple glazing, roof insulation, draft excluders, hot water tank insulation. It's just ways that you can make your house more efficient. So basically, don't lose that much heat from your home. Payback time is in years, okay? It is the cost of the installation itself divided by how much savings you get per year. Now, the way you save money by having these things is because by having them, you don't transfer as much heat out of your home. Therefore, your home stays warmer. If your home is warmer, you're not going to put your heating on. So then you're not paying money for electricity to heat your home. So it's savings that way, okay? It doesn't actually get you any money. It's by saving money. Cost effective is a word that they love to throw in, and not many people know sort of how to word it. It's when the cost of making a change, so getting double glazing, is low in relation to the resultant savings in the energy bill. So the savings you get are going to sort of outweigh the cost of it over a relatively short period of time. So for example, if you bought a draft excluder for £20, put that on your door, and that saved you £10 a year, it's not bad, you know, it'll take you 2 years type of thing. So that's what cost effective means. Now, this didn't come up last year, so I think it might this year. And it's one of those horrible ones because it's calculating the energy transferred, but the units for it are completely different to how units are for everything else. Energy is usually in joules. For energy transferred in this case, it's in kilowatt hours. And power is usually in watts, but for this, it's in kilowatts. Time is usually in seconds, but for this, it's hours. So it's quite a tricky one. If they give you it in watts, transfer it to a kilowatt. 1,000 watts is a kilowatt. If they give you it in minutes, that really being mean, you have to transfer that into hours. Now, you've got to think of that as a test, okay? So, for example, if you use something for 15 minutes, you do 15 divided by 60, that's a quarter, so it's 0.25, so don't get tricked out by that. And your answer would be in kilowatt hours. Now, they then tend to relate this to cost of electricity. This formula isn't on the formula sheet, neither is this one, by the way. So you need to sort of know this. It's quite straightforward, but it's the energy transferred times the cost per unit of electricity. That's usually given to you in the question because it changes. Energy companies change their mind weekly about what they want to charge you. So it's usually about 10, 11p. So your answer will be in pence, not pounds. So they usually ask for it in pence. Don't try and convert it into pounds or anything, just leave it as it is. So for this one, if it say cost me 10p per unit, you do 0.75 times 10, so it'd just be 7.5 pence. Okay, so that is energy transferred.